Early Saturday, the Northern Hemisphere witnessed breathtaking displays of color in the skies, courtesy of an exceptionally potent geomagnetic storm. The U.S. National Oceanic and Atmospheric Administration, or NOAA, surprised observers by issuing a rare severe geomagnetic storm warning on Friday afternoon, prompted by the earlier-than-expected arrival of a solar outburst known as a coronal mass ejection, or CME. NOAA has said that we are having a geomagnetic storm caused by a coronal mass ejection. To understand what is going on, we need an understanding of some basic terminology, so let's break this down. A CME, or coronal mass ejection, is a disturbance in the Earth's magnetosphere, caused by interactions between the Earth's magnetic field and the solar wind or other solar phenomena. These disturbances can have significant effects on technology, infrastructure, and natural phenomena on Earth. The result is the geomagnetic storm that we are currently experiencing. Geomagnetic storms are closely related to solar storms and are, in fact, a consequence of certain types of solar storm activity, particularly coronal mass ejections, CMEs, and high-speed solar wind streams. So let's discuss the relationship between solar flares, solar storms, and geomagnetic storms. Solar flares, coronal mass ejections, and high-speed solar wind streams are distinct yet interconnected phenomena originating from the sun. Solar flares are intense bursts of radiation, primarily X-rays and ultraviolet light, resulting from sudden releases of magnetic energy near sunspots. They often rapidly heat the solar plasma and accelerate charged particles. Solar storms also occur when there is a significant release of energy, but material is also released from the sun into space. This material is primarily composed of plasma and magnetic fields and can interact with the Earth's magnetosphere, leading to geomagnetic disturbances. As mentioned, geomagnetic storms result from solar storm activity, specifically CMEs and solar wind streams. They are not directly caused by solar storms, but they are closely related phenomena that result from interactions between the Earth's magnetosphere and solar activity, including solar storms. When the Earth's magnetosphere is impacted by an influx of charged particles from the sun, it can lead to disturbances in the Earth's magnetic field. These disturbances can cause phenomena such as auroras, northern and southern lights, and disruptions to power grids, communication systems, and satellite operations. This is what we are currently experiencing. So these coronal mass ejections are massive eruptions of plasma and magnetic fields from the sun's corona, the outermost layer of the sun's atmosphere. These eruptions can release billions of tons of material into space at speeds of several million miles per hour. High-speed solar wind streams, on the other hand, are continuous streams of charged particles emitted from coronal holes on the sun's surface, traveling at speeds higher than average solar wind. So we must understand the distinction that while solar flares primarily emit radiation, CMEs are massive disturbances in the solar wind that can cause geomagnetic storms when they interact with the Earth's magnetosphere. High-speed solar wind streams contribute to variations in the solar wind and can also influence space weather, albeit with less intensity than CMEs. Now that we have a little background about what is going on in the atmosphere surrounding Earth, let's look at the sun's corona and what such disturbances can do. The sun's corona is the outermost layer of the sun's atmosphere, extending millions of kilometers into space. So let's look a little more closely at the sun's corona first. We must address the intense heat of the sun's corona because despite being the outermost layer of the sun's atmosphere, the corona is much hotter than the sun's surface. The surface temperature of the sun is called the photosphere and is around 9,932 degrees Fahrenheit. The corona can reach temperatures of several million degrees, far exceeding the temperature of the surface below it. So the sun's corona is actually much hotter than the sun's surface, which might seem counterintuitive since the surface of the sun, called the photosphere, is where nuclear fusion occurs and is incredibly hot. The exact reason for the corona's extreme heat compared to the photosphere is not yet fully understood, but there are several theories. The first is that the sun's corona is highly influenced by its magnetic field. Magnetic fields in the sun's atmosphere can become twisted and stressed, leading to the release of vast amounts of energy in the form of heat and solar flares. This energy heats up the corona to temperatures much higher than those of the photosphere. The next theory is wave heating, which suggests that waves or oscillations in the sun's surface, caused by convective processes or magnetic activity, can carry energy into the corona, where it is converted into heat. This process, known as wave heating, could contribute to the higher temperatures observed in the corona. Then there are microscopic processes occurring in the corona that could contribute to its high temperature. For example, interactions between charged particles in the corona, such as collisions and plasma instabilities, can generate heat. Then, magnetic reconnection events, where magnetic field lines break and reconnect, can release significant amounts of energy in the form of heat and particle acceleration. These events are common in the sun's corona and could contribute to its high temperatures. As much as we want all the answers, understanding the mechanisms behind the heating of the solar corona is a complex and ongoing area of research in solar physics, with implications not only for understanding the behavior of our nearest star, but also for predicting and understanding space weather phenomena that can impact technology and infrastructure on Earth and in space. The next characteristic of the corona which is unique is its density. The corona is much less dense than the layers of the sun below it. It is composed of extremely hot and ionized gas or plasma, which is less dense than the denser layers of the sun's interior and photosphere. The corona is visible during total solar eclipses when the moon blocks out the sun's bright disk. During this time, the corona appears as a pearly white halo surrounding the darkened disk of the moon. The corona's faint emissions are typically overwhelmed by the sun's brightness and are not visible under normal circumstances. The corona is the source of the solar wind, a continuous stream of charged particles, mostly electrons and protons, that flows outward from the sun in all directions. The high temperatures and intense magnetic fields in the corona accelerate these particles to velocities which propel them into space. The corona is also the region where the sun's complex magnetic field lines extend into space. These magnetic fields play a crucial role in shaping the corona and governing solar activity, including the formation of sunspots, solar flares, and coronal mass ejections. Despite being one of the sun's most enigmatic regions, the corona plays a vital role in understanding solar activity, space weather, and the sun's influence on the solar system. Studying the corona helps scientists unravel mysteries about the sun's magnetic behavior, solar dynamics, and its impact on Earth and other planets. Just like the corona, the exact cause of coronal mass ejections is not fully understood, but they are generally associated with the destabilization and eruption of magnetic fields in the sun's corona. This can happen due to the following processes. We touched on magnetic reconnection. When magnetic field lines in the sun's corona become twisted or stressed, they can undergo a process called magnetic reconnection. This sudden rearrangement of magnetic fields releases stored magnetic energy, triggering a CME. Filament eruptions. Filaments are cooler, darker regions of plasma suspended in the sun's corona by magnetic fields. When these filaments become unstable and erupt, they also can trigger a CME. Solar flares are often associated with coronal mass ejections. The energy released during a solar flare can destabilize nearby magnetic fields, leading to CMEs. These explosive events are caused by the sudden release of magnetic energy stored in the sun's atmosphere. The exact mechanism behind solar flares is complex and not yet fully understood either, but it generally involves magnetic fields, magnetic reconnection, energy release, particle accelerations, and emission of radiation. Let's reiterate and elaborate on these phenomena for a moment. So now we know that the sun's surface is covered in a complex network of magnetic fields. The sun's magnetic field lines are constantly in motion. We also know that sometimes these lines become twisted and tangled due to the differential rotation of the sun because the equator rotates faster than the poles. This twisting or stressing of the sun's magnetic field lines can release a tremendous amount of energy in the form of a solar flare. In these regions where magnetic fields are intensely tangled or stressed, magnetic reconnection occurs, which is a rearrangement of the lines when the magnetic field lines with opposite polarity come into contact. This leads to the conversion of magnetic energy into kinetic and thermal energy. So this rapid rearrangement of magnetic fields also releases a tremendous amount of energy. The energy released during magnetic reconnection accelerates charged particles, such as electrons and protons, to extremely high speeds. These energized particles then travel along the magnetic field lines and collide with the dense plasma in the sun's atmosphere. As the accelerated particles collide with each other and with the surrounding plasma, they transfer their energy, causing the plasma to heat up rapidly. This heating process leads to the emission of electromagnetic radiation across a broad range of wavelengths, from radio waves to X-rays and gamma rays. This sudden increase in electromagnetic radiation is what we observe as a solar flare. Solar flares can last from a few minutes to several hours, and they can be accompanied by other solar phenomena such as coronal mass ejections. Solar flares can vary in size and intensity, from small localized events to massive eruptions that release energy equivalent to millions of hydrogen bombs. The frequency of solar flares follows an 11-year cycle known as the solar cycle, with periods of maximum activity or solar maximum and minimum activity or solar minimum. According to NOAA, the current geomagnetic storm could produce northern lights as far south in the U.S. as Alabama and Northern California. But it's hard to predict, and experts stressed it would not be the dramatic curtains of color normally associated with the northern lights, clarifying that it will be more like splashes of greenish hues. However, I have seen photos posted from Georgia, and the colors are amazingly dramatic. If you are lucky enough to see the aurora, the best views may come from phone cameras which are better at capturing light than the naked eye. The most intense solar storm in recorded history was named the Carrington event and occurred in 1859 and prompted auroras as far south as Central America and even Hawaii. It was primarily a solar storm, specifically a coronal mass ejection. The current geomagnetic storm poses a risk for high-voltage transmission lines for power grids, not the electrical lines ordinarily found in people's homes. Satellites also could be affected, which in turn could disrupt navigation and communication services here on Earth. An extreme geomagnetic storm in 2003, for example, took out power in Sweden and damaged power transformers in South Africa. Even when the storm is over, signals between GPS satellites and ground receivers could be scrambled or lost, according to NOAA. But there are so many navigation satellites that any outages should not last long. The sun has produced strong solar flares since Wednesday, resulting in at least 7 coronal mass outbursts of plasma that can contain billions of tons of plasma and magnetic field from the sun's corona. The flares seem to be associated with a sunspot that's 16 times the diameter of Earth, NOAA said. It is all part of the solar activity ramping up as the sun approaches the peak of its 11-year cycle. NASA said the storm posed no serious threat to the 7 astronauts aboard the International Space Station. The biggest concern is the increased radiation levels, and the crew could move to a better shielded part of the station if necessary. This increased radiation, however, could threaten some of NASA's science satellites. Extremely sensitive instruments will be turned off if necessary to avoid damage, according to Antti Pulkkinen, director of the space agency's Heliophysics Science Division. These geomagnetic storms can have several potential impacts on technology, infrastructure, and natural phenomena on Earth that could occur, including power grids damage. Geomagnetic storms can induce electric currents in power lines and transformers, potentially causing damage to electrical grids and leading to power outages. These induced currents can overload transformers and disrupt the flow of electricity. Communication system disruptions. Geomagnetic storms can interfere with radio communications, satellite operations, and GPS navigation systems. The disturbances in the Earth's ionosphere caused by geomagnetic storms can affect the propagation of radio waves and disrupt communication signals. Auroras. One of the most visually striking effects of geomagnetic storms is the enhancement of auroras, also known as the northern and southern lights. These colorful displays of light generally occur near the polar regions but are being seen much further south with this event. Pipeline corrosion. Geomagnetic storms can induce electric currents in pipelines buried underground, leading to corrosion and potential damage to infrastructure. Pipeline leaks can result in environmental contamination, loss of product, and potential safety hazards. If pipelines leak due to corrosion or other factors, it can definitely result in a shortage of oil, since pipelines are crucial for transporting oil and other petroleum products from production sites to refineries, distribution centers, and ultimately to consumers. There are several sun-focused spacecraft dedicated to monitoring solar flares and other solar activities, and can allegedly be used to protect Earth's infrastructures from damage, so you should be aware of these protective measures. First, the Solar Dynamics Observatory, or SDO, was launched by NASA in 2010 and is a flagship mission for studying the sun. It observes the sun in multiple wavelengths of light, providing high-resolution images and data to understand solar activity, including solar flares, coronal mass ejections, CMEs, and magnetic field dynamics. The Solar and Heliospheric Observatory, or SOHO, is a joint mission between NASA and the European Space Agency that was launched in 1995. It studies the Sun's outer atmosphere, or corona, and the solar wind, offering continuous monitoring of solar activity, including solar flares and CMEs. STEREO, or the Solar Terrestrial Relations Observatory, was launched by NASA in 2006. The STEREO mission consists of two spacecraft, STEREO-A and STEREO-B, which orbit the Sun, providing stereoscopic views of solar phenomena. This allows scientists to observe the three-dimensional structure of solar flares and CMEs. The Parker Solar Probe was launched by NASA in 2018 and is on a mission to study the Sun's outer atmosphere, or corona, up close. It aims to provide unprecedented insights into solar phenomena, including solar flares, by flying through the Sun's atmosphere at close proximity. And lastly, the Solar Orbiter was launched jointly by the European Space Agency, ESA, and NASA in 2020. The Solar Orbiter mission is designed to study the Sun's polar regions and provide high-resolution images of the solar surface. It will help scientists understand solar activity, including solar flares, from different perspectives. So we clearly have equipment to detect and monitor solar phenomena, but how do these protect us? These spacecraft dedicated to monitoring the Sun and space weather can help mitigate the impact of solar storms on various essential services such as power grids, satellite communications, and navigation systems through several key mechanisms. Early warning and forecasting allow operators of critical infrastructure, such as power grids and satellite networks, to take preemptive measures to mitigate potential impacts. For instance, power grid operators can deploy protective measures like series capacitors and transformers with geomagnetic shielding, and conducting regular drills to test response plans. By reducing power loads, adjusting grid voltages, and implementing protective measures such as deploying series capacitors or disconnecting vulnerable transformers, operators can minimize the risk of damage to transformers and other grid components. Additionally, investments in grid resilience, such as the installation of geomagnetically induced current (GIC) monitoring systems and grid topology optimization, can help mitigate the impact of geomagnetic storms on power distribution. Satellite operators can adjust satellite orientations, activate radiation shielding, and implement operational strategies to minimize exposure to charged particles and electromagnetic fluctuations. Operators can protect satellite systems from potential disruptions. Additionally, satellite designers can incorporate enhanced shielding and redundancy measures to improve satellite resilience to space weather effects. Global navigation satellite systems, GNSS, such as GPS, rely on precise timing signals transmitted from satellites in space. Solar storms can disrupt GNSS signals due to ionospheric disturbances and radio frequency interference caused by increased solar radiation. Space weather forecasts enable GNSS users to anticipate potential disruptions and implement alternative navigation solutions, such as differential GPS corrections or inertial navigation systems, during periods of degraded GNSS performance. Similarly, telecommunications operators can adjust satellite communication protocols and frequencies to minimize interference and maintain reliable communication links during solar storms. So measures can be taken to mitigate solar phenomena damage, and if damage to our infrastructures occur, it appears that it may be either deliberate or negligence in construction and maintenance. There is no reason that we should live in fear of such disruptions, but that doesn't mean that they won't be used as a means of putting the world in turmoil, which we will discuss. But first, let's look at the timing on these solar disturbances. Solar cycles, also known as solar activity cycles or sunspot cycles, typically last around 11 years. However, the duration can vary from cycle to cycle, ranging from about 9 to 14 years. These cycles are characterized by the waxing and waning of solar activity, including the number of sunspots, solar flares, and other solar phenomena. During the solar cycle, solar activity gradually increases from a minimum, characterized by a low number of sunspots, to a maximum, marked by a high number of sunspots and increased solar activity. After reaching the maximum, solar activity declines again, leading to a new minimum and the start of a new solar cycle. The most recent solar maximum was reached around 2013, marking the peak of solar cycle 24. Solar cycle 24 was relatively weak compared to previous cycles. We are currently in solar cycle 25, which began around December 2019. As of now, we are gradually progressing through the ascending phase of this solar cycle. Solar activity, including the number of sunspots and solar flares, is expected to gradually increase as we approach the solar maximum of cycle 25, which is projected to occur around 2025 to 2026. So according to experts, we are in the early to middle stages of solar cycle 25, experiencing a gradual rise in solar activity. But let's look a little closer at these numbers. If the last peak was December 2013, add 11 years to that, and that puts this peak at about December 2024, right? That means that around last quarter 2024, this solar activity could begin to decline, placing 2030 at the end of cycle 25. I find this timing a bit coincidental to other information that we've been hearing about the timing on this war between good and evil. Could his solar phenomenon be used to put the world in lockdown sometime during this peak, potentially occurring the end of 2024? I don't know, but I have heard that communications and a possible grid failure will put us into lockdown as we transition to our new future. I also heard from many that the full transition of Earth will be completed by 2030, which is the predicted end of cycle 2025. Could all of this solar disruption be clues to humanity of what to expect over the next few years? I think so. I would also like you to keep in mind that measures can be taken, and no matter what you hear or see over the coming months, there is no reason that the Earth or any of our infrastructure should be destroyed. So please don't be fearful if the power and communications go off. My suspicions are that this has all been part of considerations and that there is a new grid ready to go up at any time with free energy. Only time will confirm this, but I hope that a better understanding of this will give you both hope of a planned operation to save our world and our society. In fact, I'm betting that it's going to come back better than ever. Every time you share my videos, it builds my channel and makes it more feasible for me to continue working full-time to bring you my videos. Every time you watch my videos or subscribe, like, and comment, YouTube shows my videos to more people via their searches and sidebar recommendations. So please help me out with your participation, and we can reach others to let them know that everything is going to be all right and that they have nothing to fear. I try to cut through all the crap and lies to find the truth, and I truly believe that we have an amazing future coming over the next few years. It's an amazing time to be alive, guys. I love you all, and know that we're all going to be just fine. Thank you so much.